In this video, I'll explain first how the Gradle Enterprise Maven Build Cache speeds up Maven builds and tests. I will then introduce a mathematical model for quantifying some of the productivity and financial benefits your organization will get from caching and faster feedback cycles. Most Maven builds, whether they are small or large, are multi-module builds, where a number of modules live in the same source repository. Those modules have separate sources from each other. Here are the sources for the core module, here are its test sources, here are the sources for the export module, and here are its test sources. The same structure applies to all the other modules. Let's build this project. For the sources of the core module, there is a dedicated compile goal that compiles the sources into a specific output directory. For the test sources of the core module, there is a similar compile goal that uses a different output directory. There's another goal that runs the tests and puts the results again in a separate directory. For the other modules, the same types of goals are executed. The build is finished and it took 1 minute and 8 seconds. Let's change the code in the export module. When you rebuild the project, everything is rebuilt, including the compile and test goals of the core, security, service, and web app module, although their goals have exactly the same output they had in the previous build. And therefore, despite changing only one line of code, the build took again over a minute. It doesn't matter whether this is a local build or a CI build, the problem is the same. Everything is built from scratch, all the time, regardless of the scope of the code change, which elongates feedback cycles and wastes compute resources. How can we reuse output from previous builds to avoid executing Maven goals unnecessarily? We can consider a Maven goal to be a pure function. For a given set of inputs, it always produces the same output. For example, whenever you compile with the same sources, class path, and compiler configuration, you will always get the same bytecode. Now let's look in more detail at the compile goal of the core module. Its inputs are its sources, class path, and compiler configuration. We can use a cryptographic hash function to generate a key that is unique to this set of inputs. If I change anything in the sources, the key will change. If I change a dependency, a different key is generated. If I change the compiler configuration, we get another key. We call such a key a cache key. A build cache is simply a key value store where each key is a cryptographic hash of goal inputs. And the value is the output of a goal with those inputs. Before a goal is executed, we can check for an entry in the build cache with the same cache key. If one exists, we can safely reuse the value of the entry as the goal output and avoid doing the time-consuming work of the goal. If there's no entry, then we execute the goal and store its output in the cache, so it can be reused next time someone executes the goal with the same inputs. A cache can be used for a wide variety of goals, from compilation and testing to code coverage, Javadoc, source code generation, and check style. Let's look at how this works in practice. To enable the build cache, we need to apply the Gradle Enterprise Maven extension. An extension is a special type of Maven plugin that integrates with the Maven build lifecycle. There are various ways to add this extension. For example, whenever you start a Maven build, Maven looks for the existence of a .nvm directory in the root of the project. If it finds this directory, it looks for an extensions.xml file in this directory. That's where we add the Gradle Enterprise Maven extension. One way to configure this extension is to add a Gradle enterprise.xml file. This is where the local build cache is enabled. This is also where you can define the location of the local build cache directory, where all the cache entries are saved. The Gradle Enterprise Maven extension collects detailed data about all aspects of a Maven build execution, including the caching. This data is sent to your Gradle Enterprise server, where you can view it in the form of a build scan. We will make use of that later. On the right, you can see the local build cache directory, which is currently empty since it's the first time the cache is being used. Let's run the build again. Whenever a goal is about to be executed, the Gradle Enterprise extension calculates a cache key for that goal. It then looks for a file in the local build cache directory that matches the cache key. The directory is empty, therefore the file can't be found. We call this a cache miss. When there's a cache miss, the Gradle Enterprise extension executes the Maven goal, in this case the compilation. After the goal is executed, the extension stores the output of the goal as an archive file in the local cache directory. The name of the archive is the cache key. The build is finished. This build has seeded the cache so that future builds will be faster. Let's go to the build cache directory, which you also see on the right, and look at the content of some of the archive files to validate that they contain the output of the goals. The file that starts with F22 contains the output from the compile goal of the core module. For the file that starts with DB9, it is the output from the test compile goal of the export module. For the file that starts with C34, it is the output from the test goal of the service module, which are the test results XML files. Now let's run the build again. Before the compile goal is executed, its cache key is calculated. The local cache is searched for a file that has the name of the cache key. This file exists now. We call this a cache hit. You see in the build log that it says loaded from the build cache. This means that the file in the build cache was unpacked into the output directory of the compile goal instead of executing the compile goal. This is much faster. The build is finished in 3 seconds instead of more than a minute. When we look at the build scan of this build, it gives us detailed information about the caching history. The cache key is captured, as well as whether this cache key was found in the cache. It shows how long it took to unpack the entry into the Maven output directory and how much time was saved compared to executing the goal. Gradle Enterprise also provides the build cache as a remote service, so that the output from Maven goals can be shared across the organization. To connect your build with a remote cache, you need to enable the build to read from it. If you also want to publish build output to the remote cache, you need to explicitly enable this as well. Usually, only CI builds are configured to publish to the remote cache. A way to do this for Jenkins, for example, is with a conditional expression like this. For this demo, we enable all builds to publish to the remote cache. We now delete all the entries from the local cache and run the build again. Before the compile goal is executed, its cache key is calculated. Then the local cache is searched for a corresponding entry. There is none. Then the remote cache is queried. We can see this query in the event log of the remote cache node. The results of the query is a miss, and therefore the goal is executed. Then the output of the goal is not just stored in the local build cache, but also in the remote cache. The build is finished, and the remote cache is now seeded with cache entries. Once more, let's delete all the entries from the local cache and run the build again. Before the compile goal is executed, its cache key is calculated. No entry can be found in the local cache. This time, we get a hit from the remote cache. Therefore, the goal is not executed. Instead, the entry is downloaded to the local cache and unpacked into the output directory of the goal. The build is finished in 8 instead of 65 seconds. Often modules are interdependent. In our case, export depends on security. What happens if we change the source code in security and run the build again? We see that for the core module, the output for the compile and test goals are loaded from the cache. The same is true for service and web app. Security is recompiled and retested, as is the export module. The build finished in 29 seconds instead of 65, because only 6 instead of 15 compile and test goals needed to be executed. When we do a detailed comparison of this build with the previous build, you can see that those 6 goals had changed inputs. For the compile goal of security, the security util source file has changed. For the test compile goal, the corresponding class file has changed. For the compile goal of the export module, the content of the security jar file has changed. This is also true for its test goal. All of those changed inputs have led to different cache keys, for which there was no entry in the build cache. You see how the build cache leads to faster builds while still reliably producing correct output. When you look at the build log, you can see that certain goals are never cached. In a build scan, we can see this more clearly. There are a number of goals that are marked as not cacheable. There are various reasons for that. Obviously, it doesn't make sense to cache the clean goal. But what about the resources goal? What this goal does is to copy files from the source main resource directory into the target classes directory. Caching those files and then copying them from the build cache into the target directory will not be faster. You would just have the overhead of storing them in the cache. That is why they are not cached. The same is the case for archive goals like creating jar files where you basically copy the .class files into an archive file. In other words, goals that are computationally intensive benefit the most from caching. Those are usually the goals that consume most of the build time. Examples for that are compilation, testing, and other code quality checks, as well as source code generation. Let's talk about build time behavior in more detail. This graph shows the time it takes to fully build a project with n modules. We assume here that all modules have the same build time and that the build time per module is 13 seconds, as it was for our example project. The build time is growing linearly with the number of modules, and the slope is the build time per module. Our previous example project had 5 modules. A full build of such a project, as we have seen, takes about 65 seconds. If we added another 45 modules with the same amount of code and tests, a full build would take 11 minutes. Let's look at the build time when a change only affects one module. For example, a pull request build on CI where only one leaf module has changed. Without a cache, the graph is the same. The build time for one module change is the same than building all the modules. You can see why building Maven projects is expensive. A small change for a 50 module project will cost the same 11 minutes of build time than when everything has changed. With the build cache, the build time for a one module change is also growing linearly. The OM parameter is the cache overhead. This is the time per cached module to retrieve the output from the cache and run the non-cacheable goals. It is usually orders of magnitudes faster than building a module. For our example project, the overhead is half a second. This is only 4% compared to building it. Therefore, for a 50 module project, the build time for a one module change is only 38 seconds instead of 11 minutes without the cache. You would see a similar behavior for changes that affect 3 modules or 10 modules. The reason why the saving potential from a cache is so enormous is that for most projects, most of the changes per build affect only a smaller subset of the codebase. How much are those savings worth? This graph shows how the build cache reduces the time developers are waiting for builds to finish. It is measured in engineering years per year. We assume here that in average 30% of the modules need to be rebuilt. This graph is for a 10 module build with 13 seconds of build time per module. With 10,000 builds per week, you would be getting back 7 engineering years over the course of a year. With 1,000 builds, 158 engineering days. Getting back 158 engineering days per year would be marginal for a team of 1,000 developers, but very substantial for a team of 5. If the build time per module is 60 seconds, with 10,000 builds per week, you are getting back 34 engineering years per year. If there are 30 instead of 10 modules, it is 102 years. Those time savings from the cache translate directly into cost savings for your CI cloud because of the reduced compute load from caching. Pause the video here if you want to look at the math behind the graphs we have shown. The benefits from faster feedback cycles go way beyond compute resource savings and reduced waiting time. Developers have less context switching and an increased state of flow. With faster builds, developers build more often. This means smaller change sets, leading to less merge conflicts and faster troubleshooting of failed builds. A higher build frequency also means more frequent and earlier feedback, leading to less late integration problems and less bugs shipped to your customers. And yes, you also ship your software faster. So far, we looked at projects where the amount of code and tests were growing with the number of modules. What if you have BFMs, where a lot or all of the code is in a single or few modules? Let's say you have all your code in one module that takes 10 minutes to build. In this case, the build time is always 10 minutes, with or without a cache, be it a small or big change, it doesn't matter. What happens to the build time if you split the code into 2 equally sized modules? Let's say module 2 depends on module 1 and half of your changes occur in module 1, the other half of the changes in module 2. With plain Maven, it doesn't make a difference. With the build cache, it does. This will speed up your average build time by 1.3. A change that affects only one module will be 2 times faster to build. Let's divide the code into 10 modules and assume that on average 30% of the modules need to be rebuilt. Now your average build time is around 3 minutes, which is 3.3 times faster. A single module change is 10 times faster. As you split the code across more modules, the percentage of the modules that need to be rebuilt will decrease. If you split the code across 20 modules, you might only need to rebuild 20% of the modules per build. Now your average build time is 2 minutes, which is 5 times faster. The build for a change affecting only one module would be 20 times faster. In sum, for projects which are not modularized at all, even very coarse-grained modularization will give you much faster builds once you start using a cache. For most projects, a build cache substantially speeds up build time out of the box. With better modularization, you can make it even faster. Pause the video here if you want to look at the math behind those numbers. I hope I could convince you that the Maven build cache empowers you to instantly make a major impact on the speed and the quality in which your team delivers software. For you, this could mean giving every developer back half a day per week or more in lost productivity. And for your company, this can mean millions of dollars of additional R&D capacity. The Gradle Enterprise Build Cache saves the Spring Boot team, in average, 1 hour and 15 minutes of execution time for every CI build they run. Many of the world's leading technology-driven brands have found Gradle Enterprise to be a game changer and a no-brainer. Give it a try, we think you'll agree.